Okay, so today we're going to look at a little more advanced topic. We're going to introduce a couple really important theorems, the remainder and the factor theorems. Okay, now what this is about, these are related to ways that we can analyze polynomials. We can evaluate polynomials, but most importantly, it's going to help us solve polynomial equations that we otherwise can't solve at this point. Okay. So let's do a little bit of review here, first of all. If we look at just some examples, numerical examples, no variables, just numbers. If we take the quotient 25 divided by 4, right? Well, that's equal to 4 goes into 25 6 times with a remainder of 1. That's what remains over the denominator. So I get 6 plus 1/4, 6 1/4, which is 6 plus 1/4, right? The remainder is 1. If I divide 32 by 4, I get 8. Okay, what's the remainder? 0. I could, if I wanted to, write it as 8 plus 0 over 4. That'd be kind of silly though, right? Wouldn't need to do that. The remainder is 0. So answer a question for me. Is 4 a factor of 25? How do you know right away? Because I have a remainder. Exactly. If there's a non-zero remainder, then it's not a factor. Is 4 a factor of 32? Yeah, the remainder is 0, so it is. Okay. Well, we can apply that same thinking, obviously, to quotients of polynomials. It doesn't have to just be numbers, right? So we could look at something like this. If we're going to look at, we want to know, is x minus 2 a factor of 2x squared plus 3x minus 12? Well, to find out, we would just see what the remainder is, right? So if I divide these out, what's the remainder going to be? What's the easiest way to divide those? What's the easiest way to simplify that quotient? Long division or synthetic division? Synthetic, yeah, because look at the bottom, x minus 2. So if we go through synthetic division, my coefficients are 2, 3, negative 12. The number that goes out front would be the 0 of that denominator, right? Also the 0 of that factor, right? And so we get 2, we just drop down the 2, multiply by 2 and get 4, add and get 7, multiply and get 14, add and get a remainder of 2. And so I can see right away, nope, it's not a factor. I don't even have to write any of that stuff out. The fact that I get a 2 in the remainder box when I run it through synthetic division tells me, nope, no dice. Okay. Now, I've got another question for you here. This is, you don't know this yet, but just kind of use some intuition and see if this makes sense to you. So what if we're going to say P of X is equal to that original yellow polynomial? Can anybody surmise, what do you think the value of P of 2 is going to be? If I evaluate the function P at X equals 2, what do you think the output is going to be, the value of the Y value or the value of the function? What do you think? Any guesses? We could just plug it in, couldn't we? Right? So just do that real quick. Plug it in, just plug 2 in for X and do the mental math and tell me what you get. You get positive 2, don't you? Yeah. Okay. And we can see that here on the graph, can't we? Right? This is a graph of P of X. If I evaluate the function at X equals 2, look, the output is 2. The Y value is 2. Okay. Where do you think that comes from? How could I have maybe not had to have plug in 2 and go through all that mental math? How could I have known what the output was going to be? Any guesses? What do you think? It's the remainder. Yeah, it's the remainder. Okay. Okay, that's an important connection. Hold that thought. Okay. Let's try another one. Let's just make sure this works. So if I take this polynomial, the yellow polynomial, and I divide it by x minus 1, well, I end up getting, if I do the synthetic division, I get the answer 2x squared plus 7x minus 4 plus negative 18 over x minus 1. Most importantly, the remainder is negative 18. Okay. What happens if I graph that polynomial? That's P of X, let's say, the yellow polynomial. Here's a graph of the yellow polynomial. It's cubic, so it curves all over the place. What if I plug in 1, the number that was out in front of the synthetic bracket? Okay, what if I plug that in? Oh, look at that. The output when x is 1 is negative 18. Huh. What do you know? Oops, I didn't want to do that. I wanted to do that. There we go, right? So it's negative 18. That's what was in the remainder box, and that's the value of the function. Again, right? So we got this major connection going on here, right? There's a lot of stuff, and you have to really think about this to soak all this in. Okay, first of all, how how do these two things correlate? Well, right now, we just see this as, okay, the number that we would put in front of the synthetic bracket to do synthetic division, we get that from the denominator. Excuse me. Right, the denominator is x minus 1, so the 0 of the denominator is positive 1. Right? Remember that we've been doing that for a few days now, right? So that's how we get this 1 there, right? When I plug that in, though, and I get a remainder of negative 18, that's telling me something really cool. It's telling me that the coordinates of that point are 1 and negative 18. Here, let me do this, just so we can kind of color code that. What color was the 1 up here? It was blue, okay? It was cyan, you're right, cyan. And the negative 18 was magenta, that's what that was, right? Magenta. Okay, everybody see that? That's pretty profound. That tells us something really important. We got lots of connections. Okay, one connection is that if it's the polynomial remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is the value f of k. Okay? Where did the f of k come from? Well, think what we did earlier. We said that when we use the zero product property, didn't we say that if I had the factor x minus k, then using the zero product property, the 0 that came out of that was k, right? Okay, so we can also make this association between a factor of a function and a 0 of a function, right? Okay, so we got all this stuff going on. This is pretty big, though. That's the trick we just used, right? The 0 of that factor, 0 of the denominator is k. If I input that into the function, whatever the remainder is, that's the value of the function at k when I plug it in. So synthetic division, what we've always called synthetic division, and we've used to divide polynomials so far, right, is also a type of synthetic substitution or synthetic evaluation. It allows us to plug a value into a function and quickly kick out an output answer, right? Whatever's in the remainder box is the value of the function when we input that outside number synthetically. Okay, give me 1 to 5 on that. Does that make sense? Kind of getting the hang of that a little bit? Okay. All right, so I'm going to mix the order up here just a tiny bit. Before we go through the proof, I'm going to have, you guys want to, you think you're ready to try this, or should we go through this together? Like if I asked you to use synthetic evaluation or synthetic substitution to find f of negative 1, give me thumbs up or down. Would you know how to do it? Okay, I'm not seeing a ton of thumbs up. Let's do this one. Got a few. Let's do this one together. Okay. So that's telling me this is the number I'm inputting, right? So I'm going to use this synthetic process here. So I'm going to make my bracket. First thing is, what number goes outside? Negative 1. Yeah. The value that I'm inputting into the function corresponds to the outside number, right? Okay, what are my coefficients going to be? Let's put those, we'll make those blue. What are my coefficients going to be? -1. No. Got to be 0, right? Okay, let's pause on this for a second. Here's a good trick. What's the, everybody show me with your fingers, what's the degree of f of x? Yeah, good, it's 5, isn't it, right? Because x to the 5th, right? The degree is 5. So then how many columns would I need if I were doing long division, or how many coefficients or columns, whatever you want to think of it, do I need for synthetic division? If the degree is 5. 6, right? How come? Because I need one column for each power of x plus the constant. There you go. Constant is the 0 power of x, right? So we're always going to have one more coefficient in our synthetic bracket, or one more column, if we're thinking division, than the degree every time. So if we're not getting, I should anticipate I need to get 6 numbers in that top row. If I don't get 6, I missed one. I missed a 0 coefficient in there somewhere. Okay, so where do my 0 coefficients pop in? X cubed, right? So that's the x cubed coefficient. That's a 0. What's next? 0, because there's no x squared term. What's next? And finally, okay, and then remember that my remainder box, which is really important here, that's kind of what we're looking for, isn't it? My remainder box is below the constant, right? Below the last number. Now, if our last term had been -5x, what would my last number have been in that row? Would have been a 0, wouldn't it? Yep. And the remainder box would have been below that 0. Okay. So now we just do that synthetic process like we always do. What do I do first? Drop down the -1. So what goes there? 1. Multiply. Now what goes there? 0, because I'm adding, right? Okay. So what goes there? 0, right? What goes there? Ta-da. Okay. See how we're doing? See how we got this? Okay. Okay. Okay, you might be asking, now maybe you were too polite to ask, maybe you haven't just asked yet, but you might be thinking, well, God, that took longer than just plugging in -1, right? It probably did. But what if that were a -57? This would have been a lot faster, wouldn't it? Yeah. Okay. Yep. Because it's what is this polynomial? If I say all the terms, it's -x to the 5th minus x fourth plus 0x cubed plus 0x squared minus 5x minus 7. Okay. Okay. Because you always start out. Remember that here's a way to think about it. In order to kind of start the chain reaction, you have to drop a number down below the bracket. Once you drop a number below, it all starts rolling, right? Anytime a number shows up, you multiply and add. So again, you multiply and add, right? Okay. Okay, so let's. You want to do one? Okay. Yeah. Here, I'll give you one. Let me make one up. Go. That today. We got to get through lots of stuff. Here we go. So let's look at a proof of what I just showed you. It's important for you guys to see some proof every once in a while. We don't do enough proof probably in high school anymore, but we're going to do a little proof today. You guys are going to see this. Let's just walk through this. We want to prove this polynomial remainder theorem. Okay, so what does this mean? So if we want to do something completely general, right? We're not going to be specific at all. If I take some polynomial, call it p of x, divided by x minus k, right? K is, some number. We know that's going to always end up equaling some polynomial, call it q of x, plus some remainder, which is going to remain over the original denominator, right? Okay, it has to fit that form. We don't know what specifically p of x and q of x are. We don't even know what k is, right? But we could plug in values and do a problem, and it would look like that. Our answer would. Agreed? Okay. So let's do something to that. Let's multiply both sides by the factor x minus k. If I distribute the x minus k on this side, I'm going to get x minus k times q of x plus x minus k times that quotient, right? The remainder fraction. And I get a lot of cancellation. The x minus k's cancel there, and they cancel there. It starts to look much cleaner. I end up getting p of x is equal to x minus k times q of x plus r. Okay? All right, well, the whole point of this was we wanted to prove the remainder theorem. So if we evaluate this at k, why k? Because k is the zero of the denominator, right? So if we evaluate this at k, what has to happen? Well, when I plug k in, x minus k, when I let x equal k, that becomes k minus k, which is 0, right? So I get 0 times q of k. I don't know what q of k is, but I know what 0 times q of k is. It's 0. So I get p of k equals 0 plus r. So p of k equals r. We just proved it, right? There it is. We just proved that synthetic substitution has to work. Okay, amazing. And it works for all cases, right? It was totally general. Okay. Now, let's take a look at something. Let's look at one more of these together, and then we're going to move on to just a slightly new application of this, very slightly. Okay, so I want to know, is x plus 1 a factor of, we'll call it p of x, that yellow polynomial? How would I know? Well, I can use synthetic, right? But how would I know if it's a factor? If it doesn't have a remainder, right? So all we have to do is just run it through synthetically and see what the remainder is. That's it, right? Okay, so what would I do then? First thing I'm going to do is drop, right? Everybody gets those are the coefficients in the top row. -1 is the 0 of the denominator, right? So if I drop the 2 down, yeah, I'm going to get 2 times -1 is -2. If I add, I get 3, right? 3 times -1 is -3. If I add, I get, oh, I didn't want to do that. Let's see, I want to do that. I get -14. And then that gives me, the first part of my polynomial answer. Not that I really care about it for this problem. And then -14 plus 14 is 0. And so I just get that answer, right? It does go in because there's no remainder. Okay, good? Everybody good? Well, we'll get more of that, but not today. Maybe we will. I don't think we'll get that far. So p of -1 is then, of course, what? Well, we already know the answer. 0. Yep, it's got to be 0, doesn't it? Okay. 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 All right, so then we get this big connection going on. We get these 3 interchangeable kind of intertwining concepts that all go together. Right? We know that if we divide out this quotient, yellow divided by blue, and the remainder is 0, well, that tells us that the value of the function, if I evaluate the yellow at the blue 0, right? The 0 of the denominator, which is -1, I know I'm going to get 0. And it also means that if I do synthetic division with you can't see that, but that's a -1 out front there, right? -1 goes with the x plus 1 in the denominator. I'm going to get a 0 in the remainder box. All those things go together, don't they? Okay. And of course, that means that if I look at the function, when I plug -1 in, I get 0 as an output, and so it's an x-intercept, right? Real zeros always correspond to x-intercepts, so there's another connection there. When we know that -1 is a 0, we also know it's an x-intercept on the graph. Okay, all this stuff gets connected. So let's look at this just in a little bit of writing, so you can just kind of focus on the text here for a second. So if x minus k is a factor of p of x, then r must also equal 0. Those go together, right? Recall, we've already talked about this, that the zeros of a function are the places where the function is 0, right? Okay. So in other words, k is a 0 of f of x if and only if f of k is equal to 0, right? Okay. I know that k is a 0 of f of x if and only if when I input k into the function, I get out 0. Okay. We've seen that dividing by a factor always produces a remainder of 0. So we also have the factor theorem coming out of this that's connected. K is a 0 of f of x if and only if x minus k is a factor of f of x, right? All that stuff just gets connected together, right? Okay, give me 1 to 5 on this. How are we doing? It's a lot of stuff. You're probably going to have to look back at this, but you feeling like it's trending up for you a little bit? I mean, if it's not a 5, maybe it's moving that way at least. Okay. Any questions? Okay, this will help. Let's go through one more example. Okay, I'm going to remind you about something that you already know really well. Find the zeros. This is an application of the factor theorem. If k is a 0 of f of x, if and only if x minus k is a factor of f of x, find all the zeros of f of x equals x squared minus x minus 6. Okay? You guys have done this 1,000 times, but you've never probably made this exact connection. Oh, it's been 1,000. I bet it's been close. How would I solve that? No. Oh, I'm gonna factor it, aren't I? Magic numbers, yeah, right. Okay, so what's my first factor? Or I mean, what are my magic numbers going to be? Okay, I'm going to get negative. Whoops. I'm going to get -3 and +2. Okay. Well, we always called this the zero product property, but the zero product property is really just a corollary of the factor theorem, right? If these are factors of the function, then what are the zeros going to be? 3 and -2. You guys have been doing that forever, right? So you already know the factor theorem. You've been applying it forever. Whoops. And those are together. Aren't those just the zeros of f of x? How about that, right? Isn't that cool how that all goes together? Okay. Oh, why'd that show up twice? There we go. Okay, how about this one? You guys have done problems like this too. How could we build a simple polynomial with those zeros? What would we do if I want to build a polynomial f of x? Whoops. how could I build a polynomial from those zeros? It's just a factor theorem. Ah, okay, yeah, look, exactly. If this is a zero, if k is a zero, what's the factor? X minus k, right? So we go back again to this factor theorem. K is a zero of f of x if and only if x minus k is a factor. If and only if is the same thing, by the way, as a two-directional arrow. So each one implies the other. It means that k is a zero of f of x if, or if x minus k is a factor, or you go the other way and say x minus k is a factor if k is a zero. It goes both ways equally. Okay, they go together. They have to go together. So then over here we know that if x equals 2 is a zero, x minus 2 is a factor. You guys have done this. If negative 3 is a zero, what's the factor? Good. And if 0 is a factor, is a zero? What's the factor? X minus 0, which we wouldn't even write, would we? See what I'm saying? And we just multiply those out and we get the function. Okay? Yes, sir. Yes, ma'am. Sorry. Yeah, oh, we would. Yeah, we wouldn't write this part. We wouldn't write that part. Yeah. Okay. Yep. No, you just put the x in front. But what you're probably going to do is probably going to tell you to write it in standard form, so you're just going to FOIL it out anyway, right? But you guys have already remember we had an assignment with a bunch like that, didn't we? Yeah, I thought we did. Okay, here's everything in one page for your notes that we just went through. Okay, now let's do one more. This is going to be a little bit of a push, but see if we can do this one. So this is really cool. At least we'll get a start on this. Now, I want you to appreciate this question for a second. It's telling us to solve this equation. Well, first of all, solving an equation, we already know what the rules are for solving polynomial equations. If the polynomial is bigger than cubic, we have to factor it until our factors are quadratic or smaller, right? Till we get x squareds, x squareds or x's in our factors, okay? And then we could apply the zero product property, right? However, there's no way this is going to work for us at this point because the only technique we have for factoring a four-term polynomial is factoring by grouping. Okay, is this going to work? Thumbs up or down for grouping? Thumbs down. Yeah, look, it's not going to work because the ratio of the first two terms is not equal to the ratio of the second two terms, is it? You can just look at the coefficients. 1 over 2 is obviously different than negative 5 over negative 6. So grouping will not work, right? Okay, now they are giving us a hint. They're telling us here something important. They're telling us that 2 is a 0 of f of x, right? And that's f of x right there. Let's do it this way. 2 is a 0. We'll just do that. Okay, so they gave us something, and you might be thinking, okay, well, yeah, Mr. Ray, they gave us something. But we will actually be able to, I'm going to show you guys, it won't be this week, but I'm going to show you something called the rational root theorem really soon. And the rational root theorem will allow us to find all the rational zeros of any polynomial. Okay, it's a little bit of a process, but we can find it. And 2 is rational, isn't it? 2 is equal to 2 over 1. It's written as a fraction. So we could still do this problem even if they didn't give us the 2. We could find it. Okay, so what do we do? What do we do? Well, we're starting off with our original polynomial, right? We'll call this our original polynomial. X cubed, it's f of x, right? X cubed plus 2x squared minus 5x minus 6. We're trying to solve the equation. When does that equal 0? We've got to factor it, right? We've got to factor this to solve. Do I know any factors of the blue polynomial? I know if 2 is a 0, what's the factor that goes with that? Well, x minus 2, right? The factor is x minus 2. So if 2 is a 0, then that's telling us that x minus 2 is a factor, right? Okay, so let's do something here. Let's just take this blue polynomial. We're going to do a little bit of kind of side work here for a second. We're going to take this blue polynomial x squared plus x cubed plus 2x squared minus 5x minus 6, and we're going to divide that by the factor x minus 2. What's the remainder going to be? Everybody, what's the remainder going to be? If it's a 0, what's that tell us? 0, right? This is telling us then that f of 2 equals 0, which is telling us that the remainder is 0, right? Okay, everybody give me 1 to 5 on that. Everybody see that? Okay. So we know that then this is going to equal, guaranteed, this is going to equal some function over here, some polynomial function with no remainder. I just have to find out what that polynomial function is. I can do that synthetically, right? So let's at least get that far. So if I make my synthetic bracket here, and I put in the blue coefficients, they're just 1, 2, -5, -6. My green 0 is 2, right? And I already know that my magenta remainder is going to be what? It's got to be 0, but we need to know what goes there, right? Okay, so what is that? We can do this synthetically really quick. We drop the 1 down. 1 times 2 is 2, plus 2 is 4, times 2 is 8. Am I doing that right? Yep. So I'm getting 3, and then I'm getting 6, right? Okay, good. So what's that tell me then? That tells me that the yellow polynomial is going to be x squared plus 4x plus 3, doesn't it? Right? Okay, so we could go back up here, and we know this is x squared plus 4x plus 3. Well, doesn't that just mean that the blue polynomial factors into x minus 2 times the yellow polynomial, right? If I multiply each side by x minus 2, that's what we get, right? We get right? All we did was we just factored the blue polynomial. Look, it breaks off into this yellow factor and this green factor, right? Well, look at that. Problem solved, right? Now we broke it down a little bit. I could factor the yellow one a little bit further, couldn't I? What does that factor into? X plus 3, x plus 1 times x minus 2 equals 0. So what are my solutions? What are the other zeros of this function? Well, there's the one we were given, right? X equals 2. We were gifted that one, but the other ones are -1 and -3. How about that? Okay, we got them all, right? And that's what we wanted to know. Solve the equation. Well, there are my solutions. Okay, there are the zeros of that original function. Okay, give me 1 to 5. Okay, wow, that's pretty good. Good.